Welcome to another module in this massive open online course on probability and random variables for wireless communications. In the previous modules, in the recent previous modules, we have seen random processes and a special kind or a specific subclass of random processes, that is wide sense stationary random processes. We have defined this property of wide sense stationarity of a random process. Now let us look at another interesting property of a wide sense stationary random process, which is known as the power spectral density, and this is a very important quantity for a wide sense stationary random process. So what we want to start looking at today is another new and important concept, which is the power spectral density, and I am also going to abbreviate this as PSD, the power spectral density. And what is the power spectral density? We have already seen that for a wide sense stationary random process, for a WSS, which is basically for a wide sense stationary random process, we have the autocorrelation function, which is defined as the expected value of x of t into x of t plus tau, which is equal to r xx, that is depends only on the time shift tau. That is the correlation at two time instants. That is, if we consider a random process xt, the correlation at two time instances t and t plus tau, that is expected value of xt times xt plus tau depends only on the time shift tau and is denoted by rxx of tau. And this is, remember, this is for a random process, that is the random process for a random process x, for a random process xt. Now for this random process with this autocorrelation function, remember this is also known as the autocorrelation function, and this depends only on the time shift. Depends only on the time shift tau. That is, remember, this depends only, the autocorrelation depends for a wide sense stationary random process, depends only on the time shift tau and not the specific time instant t. And now for this wide sense stationary random process, we can define the power spectral density, and the power spectral density is simply given as the Fourier transform of the autocorrelation function. So the power spectral density, which is denoted in the frequency domain, this is naturally the spectral density, so it is defined in the frequency domain. So the power spectral density or the PSD of a wide sense stationary random process x of t is defined as, it is denoted by Sxx of f, this is the power spectral density, and it is defined as the Fourier transform of the autocorrelation function, that is integral minus infinity to infinity rxx of tau e to the power of minus j 2 pi f tau d tau. So the power spectral density, the PSD, what do we have over here? We have the PSD, the power spectral density is basically equal to, what is this equal to? This is equal to the Fourier transform Fourier transform of the autocorrelation of the autocorrelation function R xx of tau. So, the power spectral density Sxx of f, it is in the frequency domain for the random process x of t at frequency f is defined as the Fourier transform of the autocorrelation function R xx tau, that is integral minus infinity to infinity R xx tau e to the power of e raised to minus g 2 pi f tau d tau. Okay. So, naturally now using the inverse Fourier transform, one can say that the autocorrelation function is the inverse Fourier transform of the power spectral density. Since the power spectral density is the Fourier transform of the autocorrelation, so naturally it follows that the autocorrelation is the inverse Fourier transform of the power spectral density, and therefore I can also write, so naturally, so PSD, the power spectral density, is the Fourier transform of R xx tau, therefore the autocorrelation therefore the autocorrelation that is R xx of tau equals inverse Fourier transform of the power spectral density Sxx of f, and this can be denoted as R xx of tau equals integral minus infinity to infinity Sxx of f e to the power of j 2 pi f t df, that is integration with respect to f, since this is the inverse Fourier transform. So, autocorrelation, the autocorrelation function R xx tau is the inverse Fourier transform of the power spectral density Sxx f, which is basically integral minus infinity to infinity Sxx f e to the power of j 2 pi f tau df, that is integral with respect to x f over the frequency domain. So, this, let me just clarify this again. So, autocorrelation this is equal to inverse, the inverse Fourier transform inverse Fourier transform of the power spectral density. Further, some interesting properties of the power spectral density can be shown, which I am not going to prove here. Properties of the power spectral density. One is it is a power, so naturally it can be shown that the power spectral density, because it is associated with power, it has to be greater than or equal to 0, that is the power spectral density is greater than or equal to 0. Further, naturally it is greater, it is a power, so it has to be a real quantity, right. It cannot be a complex quantity, since it is related to the density of power. This is also a real quantity, it is real, so it is a real quantity, it is greater than or equal to 0. Further, it is symmetric about the frequency domains. Further, it is symmetric in the sense that Sxx of f equals Sxx of minus x. So, we are saying that the power spectral density is basically a real quantity which is always greater than or equal to 0, and it is also symmetric, that is the power spectral density Sxx at f is equal to the power spectral density Sxx at minus f. Okay. And another interesting property, if you can look at it from this integral for the inverse Fourier transform, we have Rxx tau is the inverse Fourier transform of the power spectral density. Now, if I set tau is equal to 0, so now if I set tau is equal to 0, what I have is that setting tau equal to 0 in the inverse Fourier transform above, we have Rxx of 0 is the inverse Fourier transform evaluated at tau equal to 0, that is Sxx of f e raised to j 2 pi f 0 df. Now, e raised to j 2 pi f 0 is 1. So, therefore, we have Rxx of 0 which is equal to integral minus infinity to infinity Sxx of f times e raised to 2 pi j f 0, this is 1 times df. Now, we can clearly see Rxx 0, that is the autocorrelation at tau equal to 0, this is expected x t square, this is the power of random process x t, that is what we have seen. This is the power of the random process x t, and this is simply integral of the power spectral density over the frequency domain. This is integral, this is simply the integral of the power spectral density over the entire frequency series. That is what we are seeing is Rxx 0, that is autocorrelation of the random process at delay tau equal to 0 is equal to integral minus infinity to infinity Sxx f df, which basically Rxx 0 is the power of the random process x t, which is basically equal to the integral of the power spectral density over the entire frequency domain, or basically the area under the power spectral density from minus infinity to infinity. Okay. So, that is basically the power of the random, another way to express, another formula for the power of the random process x t in terms of the power spectral density Sxx of f. And not only that, there is another interesting property of the power spectral density which can be explained as follows, that is, if we want to find the power in a frequency band omega f1 to f2, so let us consider a power spectral density Sxx of f. So, this is my power spectral density Sxx of f, and I want to find the power in frequency band f1 to f2. So, I want to find the frequency power in the frequency band f1 to f2 for corresponding to this random process x t. So, consider frequency band f1 to f2. Consider the frequency band f1 to f2, and we can ask the question, what is the power of random process x t in the frequency band f1 to f2, and the answer to the question is very interesting. The power in the frequency band f1 to f2 is basically the area under the power spectral density from minus f2 to minus f1 and f1 to f2, and therefore, this power in the frequency band power of random process x t in spectral band f1 to f2, this is equal to, what is this? this is equal to integral minus f2 to minus f1 sxx of f times dx df plus integral f1 to f2 sxx of f df. In other words, the area under the power spectral density from minus f2 to minus f1 and f1 to f2, this area under the power spectral density. So, this, and as you know, sxx of minus s f is sxx of f, and therefore, this is equal to basically twice integral f1 to f2 sxx of f df, and this, what is this? We are saying this is the power in the random process. This is an interesting property, power in random process xt corresponding to frequency or the spectral band this is the power in the random process corresponding to the spectral band f1 to f2. So, one can ask, so the total power is basically the integral of the power spectral density over the entire frequency band, that is minus infinity to infinity, and the power of the random process xt corresponding to a particular spectral band between f1 to f2, that is corresponding to the bandwidth f2 minus f1 between frequencies f1 and f2 is twice the integral from f1 to f2 of the power spectral density sxxf multiplied by df. Yeah. So, the power spectral density integral twice of the integral of the power spectral density between f1 and f2 yields the power of the random process in the spectral band f1 to f2, and that is a very interesting result, as we are going to see in an application shortly. So, what we have seen in this module is basically we have seen various aspects of the power spectral density. We have said that this is a power spectral density of a wide sense stationary random process, which is basically defined in terms of the autocorrelation function, that is the power spectral density sxxf of wide sense stationary random process xt is nothing but the autocorrelation, but the Fourier transform of the autocorrelation function rxx tau, and therefore, similarly the autocorrelation is given as the inverse Fourier transform of the power spectral density. Further, the power spectral density is symmetric and it is always greater than or equal to 0, since it is a quantity associated with the power. More importantly, what we have seen is basically that the power of the random process xt is basically the integral of the power spectral density over the entire frequency range minus infinity to infinity, and specifically the power in any frequency band f1 to f2 can be calculated as the area under the power spectral density as twice the area under power spectral density between f1 to f2, and this is, and therefore, this power spectral density is a very key quantity, very important quantity to both analyze and examine and understand the random process xt. So, we will stop this module here and look at an application in the subsequent module. Thank you very much.